It's your friend's birthday and you have shortlisted 5 items that you can gift him on this occasion. A tie, a belt, a purse, a bottle of perfume and a cap. You decide to make a combination of 2 of these items for the gift parcel. In exactly how many ways can you make this combination? Guess? Okay, just to give you an idea, some of the possible combinations are: you can choose a tie and the belt, or a tie and the bottle of perfume, or the cap and the purse, and so on and so forth. So how many combinations do you think exist? Now, do you know that your answer is simply 5C2, where C stands for combinations. You had to select 2 items out of 5 and the number of ways you can do that is 5C2, which means out of 5 we select 2. In general, if we have to select R items out of the n number of items, the number of ways we can make those combinations is NCr. Combinations means selections and NCr is the notation of combinations. In this video, we are going to learn the basics of combinations and permutations, which is a very important topic covered in maths in class 11th and 12th. Let's take up combinations first. The very first thing we need to ask ourselves is, why do we need the combination notation at all? Can't we work by pure logic? For instance, if someone asked you that in how many ways can you select 2 items out of the given 5? Our task at hand is simple. We just need to make combinations of 2 items out of these 5. So either we will select the first and second, or first and third, or first and fourth, or first and fifth, or second and third, or second and fourth, or second and fifth, or third and fourth, or third and fifth, or else fourth and fifth. These are the only possible combinations of 2 items out of 5. Let's count the possibilities. How many of them are there? They are 10 in number, as we just listed down. The same number is given directly by the combinations notation. 5C2 will give us the number of ways of choosing or selecting 2 gift items out of the given 5, which we now know is equal to 10. Now the beauty of this concept, this combinations notation, is that we do not need to draw the complete list of possibilities. 5C2 directly gives us the answer, which in this case was 10, because please understand that over here we had just a few items to select from. If the number of items or objects given to us is large, let's say 10 or so, and say we need to select 3 out of them, then the possible combinations will also be huge. It will be a huge number and we will be wasting a lot of time if we try to list down all possibilities, and we might even miss out some possibilities or double count some of these possibilities. If we are not interested in the complete list and we just need to count the number of ways of selecting R items or objects out of n, NCr makes our job simple because it gives that number directly. So combinations notation is definitely a useful concept. The next thing we need to know is the formula for evaluating NCr. So NCr is simply equal to n factorial over n minus r factorial into r factorial. So for instance, if we need to calculate the value of 5C2, over here n is equal to 5 and r is equal to 2. So 5C2 is simply 5 factorial over 5 minus 2, that is 3 factorial into 2 factorial, which is equal to 120 over 6 into 2. It simplifies to the value of 10. For ease of calculations, we should know the values of some common factorials. So let me give you a quick intro. N factorial is simply all natural numbers from 1 to n multiplied together. 0 factorial is 1 by definition. 1 factorial is just 1 multiplied by itself, so it's 1. 2 factorial is 1 into 2, so it's equal to 2. 3 factorial is 1 into 2 into 3, which is equal to 6. 4 factorial is equal to 1 into 2 into 3 into 4, which can also be written as 3 factorial into 4, and hence its value is 24. 5 factorial is equal to 4 factorial into 5. So it's equal to 120. 6 factorial is equal to 5 factorial into 6. So 5 factorial is 120. 120 into 6 is 720. 6 factorial is equal to 720. For all calculations, we do not need to calculate the values of factorials more than 6. So how do we solve a combinations notation is what we are going to do in the next section. Let's learn to evaluate the combinatorial numbers. First is HC0. Comparing it with the combinations notation, n is 8 and r is 0. Since NCr is equal to n factorial upon n minus r factorial into r factorial, its value will be equal to 8 factorial over 8 minus 0. That is again 8 factorial into 0 factorial. 8 factorial gets cancelled in the numerator and denominator and its resulting value will be 1 because 0 factorial is also 1. Next is HC8. Again, compare it to the general combinations notation. N is 8 and R is also 8. So, finding out its value, n factorial, which is 8 factorial, over n minus r factorial, which is 0 factorial, into 8 factorial. Again, 8 factorial gets cancelled in the numerator and denominator and its value is holds again equal to 1. So, in general, remember that NC0 as also NCn is equal to n factorial over n factorial into 0 factorial and their resulting values is 1. In the next question, we have to evaluate 10C1. Comparing it with the combinations notation, n is 10 and r is 1. So we will get 10 factorial over 10 minus 1, which is 9 factorial, into r factorial, which is 1 factorial. And we need to write the numerator, which is 10 factorial, in terms of the larger number in the denominator, which is 9 factorial clearly. So 10 factorial is equal to 9 factorial into 10. And we see that 9 factorial gets cancelled in the numerator and denominator. The result is 10. In general, remember that NC1, the expression can always be simplified into n factorial over n minus 1 factorial into 1 factorial. And n minus 1 factorial gets cancelled in numerator and denominator, resulting into its value, which is n. NC1 is always equal to. In the fourth question, we have to find the value of 9C2. Comparing it to NCr, n is 9, r is 2. So this will be equal to 9 factorial over 9 minus 2, which is 7 factorial, into 2 factorial. And we have to write 9 factorial in the numerator in terms of the bigger number in the denominator, which is 7 factorial clearly. So 9 factorial is equal to 7 factorial into 8 into 9. And 9C2 gets simplified to 36. In general, whenever you have NC2, we can evaluate it using factorials, but there is a refined formula that I will strongly recommend that you learn because it is used in a lot of other concepts like number of handshakes, number of diagonals in a polygon, sometimes finding out the number of straight lines that can join the given number of points in a plane and so on and so forth. NC2, there will be a similar simplification wherein n minus 2 factorial gets cancelled in the numerator and denominator and NC2 is equal to n into n minus 1 by 2 always. Now let's explore the combinations notation further. The NCRs that we use in the combinations formula are also known as combinatorial numbers and more popularly as binomial coefficients. For any given n, there are n plus 1 binomial coefficients. For example, if n is equal to 5, which means that we are given 5 objects out of which we need to select 0 or more, then r will range from 0 to 5 because the minimum number of objects we can pick is 0, or else we can pick 1 or 2 or 3 or 4 or maximum 5 objects out of 5. So r will range from 0 to 5 whenever n is equal to 5. Therefore, there will be 6 binomial coefficients for n is equal to 5. Now, how do these binomial coefficients behave? 5C0 is the number of ways of picking 0 objects out of 5. It is equal to 1. 5C1 is the number of ways of picking 1 object out of 5, and logically, also if we have to pick just one object, we will either pick the first or the second or the third or the fourth or the fifth. So picking one object out of 5 can be done in 5 ways. 5C1 is equal to 5. The formula for 5C1 gives us the same value, 5. Next comes 5C2. We just saw the value of 5C2. It is 10. Now 5C3, using the formula, we get 5 factorial over 5 minus 3 factorial, 2 factorial. And we can see that 5C2 and 5C3 will be equal, because in the calculation steps, we use the same expression. Whether you have 2 factorial multiplied by 3 factorial or 3 factorial multiplied by 2 factorial, the denominator remains the same. So 5C3 is also equal to 10. Next comes 5C4. 5C4 will turn out to be equal to 5C1. Why? Because logically thinking, whenever we select one object out of 5, we are rejecting the remaining 4 objects. Correct? So number of ways of selecting one object out of 5 is simply equal to the number of ways of rejecting the remaining 4, and therefore 5C1 is equal to 5C4 and both are equal to 5. And finally 5C5, which gives us the number of ways of selecting 5 objects out of 5. There could be only one way of selecting all objects out of the given objects, right? So 5C5 is also equal to 1. So if you have a look at the binomial coefficients, the coefficients which are equidistant from both ends are equal. So 5C0 we can see is equal to 5C5. 5C1 is equal to 5C4. 5C2 is equal to 5C3. Isn't it? And the second important observation is that the first and last binomial coefficient is always equal to 1. And these binomial coefficients first increase in value and then decrease in value. So somewhere around the middle, they take the maximum value. Now we come to a very important inference. Whenever we select r objects out of n, we reject the remaining n minus r. Therefore, the number of ways of selecting r objects out of n is equal to the number of ways of rejecting the remaining out of n, and vice versa. In our previous example, when we selected purse and the bottle of perfume, we rejected the other 3 items. It is easy to see that the same will happen in all 10 possibilities in our list, and that's why 5C2 is equal to 5C3. And that's why NCR is equal to NC n minus r. Now, few quick questions. Evaluate the following combinatorial numbers, 8C3 and 8C5. In 8C3, n is 8, r is 3, so its value is 8 factorial over 8 minus 3, that is 5 factorial, into 3 factorial. We can write 8 factorial in terms of the bigger number in the denominator, which is 5 factorial. So 8 factorial is 5 factorial into 6 into 7 into 8. And 3 factorial, the value is 6. So cancelling out common numbers in numerator and denominator, we get 56 as our answer. Now let's evaluate 8C5. In 8C5, n is again 8 and r is 5. So we get 8 factorial over 8 minus 5, that is 3 factorial into 5 factorial. It is easy to see that the denominator of 8C3 and 8C5 are same in value, because in 8C3 we had 5 factorial into 3 factorial, whereas in 8C5 we have 3 factorial into 5 factorial. Their value is the same. So 8C5 is equal to 8C3. It is equal to 56. Few more. The 7th question is to evaluate 11C4. Comparing it to NCR, n is 11 and r is 4. So this will be equal to 11 factorial over 11 minus 4, which is 7 factorial into 4 factorial. Next we need to write the numerator, which is 11 factorial, in terms of the bigger number in the denominator, which is 7 factorial. So 11 factorial we know is equal to 7 factorial into 8 into 9 into 10 into 11. 7 factorial gets cancelled in numerator and denominator, and this expression gets simplified to the value of 1320. The 8th question looks a little tricky because at first glance there are 5 binomial coefficients or combinatorial numbers to be evaluated, right? But if you have a closer look at this expression, you will be able to notice that 11C4 and 11C7 they are equal in value because NCR is equal to NC n minus R. So in case n is 11 and R is 4, then n minus R is 7. So 11C4 will be equal to 11C7. So there is a slight respite here, and we do not need to calculate their values. Their values are very huge. We just calculated them in the question 7th, but we don't need to calculate them here really, right? So all we are left with is the remaining expression, which is 6C2 plus 7C1 minus 10C0. And we have already seen that there is an easier way of calculating these. Their values are very simple to calculate. 6C2 NC2 is always equal to n into n minus 1 by 2. So 6C2 will be equal to 6 into 5 by 2. 7C1. NC1s are always equal to n. So 7C1 will be equal to 7. And 10C0. NC0 as also NCN are always equal to 1. So 10C0 will be equal to 1. So simplifying them, we get 15 plus 7 minus 1, which is 21. And finally, let's try the most important application of combinations. By now, you know that combinations mean selections. A class teacher wants to form a class committee of 3 students from a batch of 20. In how many ways can she select the 3 students to form this committee? So by now you must have understood that this worded problem is a simple application of the combinations formula. 3 students out of 20 can be selected in 20C3 ways. Calculating its value, n is 20, r is 3, so we get 20 factorial over 17 factorial 3 factorial. 20 factorial can further be written as 17 factorial into 18 into 19 into 20. And simplifying the expression, we get 1140 ways of forming the committee of students. A very important thing that I want to point out here is the fact that in combinations or selections, order is not important. So if A, B and C were picked, A, B, C is counted as one combination, regardless of the order in which these 3 students got picked. The teacher might have picked up C first and then A and then B, but only the end selection of 3 people counts, not the order in which they were picked. Let's refine the same question to introduce permutations. A class teacher wants to form a class committee of 3 students from a batch of 20 and then assign them roles of a class monitor, a class prefect, and a class coordinator. In how many ways can she do that? Okay, so let me give you the simplest approach to solve this problem, for which you don't need the concept of combinations or permutations. If I were the class teacher, I would select a student for the position of class monitor first. This I can do in 20 ways because there are 20 students, and I'll select one of them. Recall that 20C1 is 20. Once I have chosen the class monitor, I would then move on to select the class prefect. Now I have 19 students left, so I can fill up this position in 19 ways. And similarly, for the position of coordinator, there are 18 students, so this position can be filled in 18 ways because I'll appoint anyone out of the remaining 18 as a class coordinator. So by using the fundamental rule of counting, together I can fill up these 3 positions in 20 into 19 into 18 ways, which is also equal to 20 factorial over 17 factorial. So that's our answer. And you won't probably believe me at this stage, but let me assure you that all permutation questions can be solved with this simple scheme. So simple to understand, isn't it? Now let's do the same question using an alternate approach, which will also highlight the difference between combinations and permutations. So to form a committee of 3 students and then assigning them roles, the class teacher needs to do 2 tasks back to back. First, she needs to select 3 students out of 20, and this we know can be done in 20C3 ways. And next, she needs to assign the 3 roles to the 3 students that she has picked, right? So let's suppose she has selected A, B and C. The first position of class monitor can be filled in 3 ways because she can assign that position to either A or B or C. Next is the position of class prefect. That can be filled in 2 ways because one student was already assigned the role of class monitor. And for third position, that is coordinator, she will be left with only one student. Together, 3 students can be arranged in these positions of responsibility in 3 into 2 into 1, that is 3 factorial ways. And 3 factorial is equal to 6. Would you like to know what are those 6 ways? Let me list them down for you. So either it is ABC or ACB or BAC or BCA or CAB or CBA. Just remember, in general, n different items or people can be arranged or placed in an order in n factorial ways. So permutations can be thought of as 2 tasks back to back. First, we need to select 3 students out of 20, which can be done in 20C3 ways. And next, we need to arrange these 3 selected students in these 3 positions and see how many orders are possible. Answer to that is 3 factorial. By using the fundamental rule of counting, together these 2 tasks can be performed in 20C3 into 3 factorial ways. And simplifying this, we get the same answer, 20 into 19 into 18, as we got from the previous approach, which I told you was simpler. So hope the difference of combinations and permutations is clear now with the help of question 9 and 10. Combinations is just selections, the order is not important. Permutations is selections and then arrangement of the selected items. Order becomes important here. Here is a quick recap of the concept of combination and permutation that we have learnt in this video tutorial. Number of combinations, the order does not matter, of n things taken r at a time is NCr. It is equal to n factorial over n minus r factorial into r factorial. Combinations means selections. The number of permutations, where the order does matter, of n things taken r at a time is NPr, which is equal to n factorial over n minus r factorial. And it is also equal to NCr into r factorial, as we saw in question number 10. Permutations means arrangements. Using the same formula of permutation, we can infer that permutation of n items, all are distinct, taken all at a time, can be done in NPn, which is equal to n factorial over 0 factorial, that is n factorial ways. So hope this video has cleared all your doubts about combination, permutation and their notations. Please press the like button and subscribe our channel for other such useful content. You can also check out our website www.ipmleap.com and drop us a comment on the video page below. We'll be glad to take up your queries. Happy learning and take care.